and research institutes like RRI and IIA, ICTS, and so on. And we have also conducted these talks in Kannada also, with the view of encouraging the usage of Kannada in higher education. This is simply because we know that our students, even teachers, face a lot of difficulty in communicating in English at the higher levels. And even the NEP also says, why not use the local languages in higher education and make the students feel confident in communicating with the faculty members, with other people also. So we have attempted to conduct talks in Kannada wherever that is possible. And today's speaker is no exception. She is a very good speaker in Kannada. So you may also interact with her later on in Kannada if you like, on this particular topic of variable stars. So before I request her to speak, I request our General Secretary, Professor P. Nagaraju, to briefly introduce the speaker. Over to you.
Thank you, sir. It is my great pleasure and honor to introduce Dr. B.S. Shylaja to my group. Of course, Dr. Shylaja obtained her MSc in Physics from Bangalore University, PhD from the Indian Institute of Astrophysics, and the PhD thesis, Wolf-Rayet Binary Stars. And she has more than 120 publications in refereed journals and 17 books. She has written more than 300 articles, several weekly columns in Prajavani, Deccan Herald, Current Science, etc. And in fact, Dr. B.S. Shylaja joined the Jawaharlal Nehru Planetarium as an educator in the year 1994. She became the senior scientific officer, then deputy director, and took charge as director in the year 2012. And her subjects of include comets, peculiar stars, and novae. She has keen interest in history of astronomy and currently working on stone inscription, translation and analysis of manuscripts of 17th century and astronomical aspects of temples, monuments, and artworks. And of course, she has introduced, after she joined the Jawaharlal Nehru Planetarium, one of the interesting course for undergraduate students is REAP. REAP means Research Education Advancement Program. And in fact, she has taught BSc students. Not only that, she is giving talks in All India Radio, TV, and she is visiting many colleges and giving talks. In fact, I know her even to our Vijaya College. She has come and given talks more than 3 times. And in fact, last 3-4 months back, we invited her to our Vijaya College retired teachers group. And I came to know that she said that she joined as lecturer in NMKRV College. After that only she joined Jawaharlal Nehru Planetarium. In fact, lot of things are there with respect to her credits. But anyway, with this brief introduction of Dr. B.S. Shylaja, I request her to go for her presentation. Madam, welcome you to present your talk to our KPA group and also other invited persons in this group. Thank you, madam. Please
Carry on. Okay.
go ahead with your talk.
Thank you for that long introduction and reminding me that I was a lecturer once upon a time, only for a few weeks.
Madam.
Okay. So as you suggested, I'm talking on the variable stars in English. All the PPT slides are all in English, but wherever possible, I'll try to use Kannada words and notations so that you feel comfortable to follow what I'm telling. Variable stars, the word itself, we had a long debate. ಕನ್ನಡದಲ್ಲಿ ಏನಂತ ಕರೆಯೋದು ವೇರಿಯಬಲ್ ಸ್ಟಾರ್ಸ್ಗೆ ಅದೇ ಒಂದು ಮೊದಲನೇ ಪ್ರಶ್ನೆ ಆಗಿತ್ತು. And we decided we will go to G.T. Narayan Rao. Fortunately, the word he had coined was very good. He said it is Chanchala Nakshatra. ಚಂಚಲ ನಕ್ಷತ್ರ ಚಂಚಲ, ಅದು ಸ್ಥಿರವಾಗಿ ಇಲ್ಲ. ಯಾವ ಥರದಲ್ಲಿ ಸ್ಥಿರವಾಗಿಲ್ಲ? ಸೊ ವಾಟ್ ಈಸ್ ದಿ ಡೆಫಿನೇಷನ್ ಆಫ್ ದಿ ವೇರಿಯಬಲ್ ಸ್ಟಾರ್? ಸೊ ವಾಟ್ ಈಸ್ ಎ ವೇರಿಯಬಲ್ ಸ್ಟಾರ್? ಇಲ್ಲೊಂದು ಚಿತ್ರ ಇದೆ, ಅಬ್ಸರ್ವ್ ಕೇರ್ಫುಲಿ. ಗೊತ್ತಾಗ್ತಿದೆ? ಇಟ್ ಈಸ್ ಇನ್ಕ್ರೀಸಿಂಗ್ ಅಂಡ್ ಡಿಕ್ರೀಸಿಂಗ್ ಇನ್ ಬ್ರೈಟ್ನೆಸ್. So this is the fundamental definition. Its variability is in respect of its brightness. So its brightness is varying. This particular photo is a very recent one by this person who holds marks at astrophotography website. It's a very good photograph, and he has given the details of how he took these photographs. It requires a lot of patience. And astronomy demands patience because clouds will always be playing hide and seek with the sky. And so ultimately he produced this wonderful photograph, which I was able to show you as a demonstration for variability. So this is where we start. There is a variable star. So it is varying in brightness. That's the basic definition, fundamental definition. So all the stars we see in the sky twinkle. Twinkling is not a variability anyway. It is attributed to our atmosphere. So what is this variability, and how did we identify that there is a particular variable star? So can we go back and see when the first variable star was identified? It takes us to the cover page, which I had shown earlier here. Here, do you see that there is a cluster here? This cluster, this is called Kritika. There is a story associated with Kritika. They are ಸಪ್ತಮಾತೃಕೆ ಅಂತ ಹೇಳ್ತಾರೆ. ಅದಕ್ಕೆ 7 ಜನಕ್ಕೆ 7 ಹೆಸರಿದೆ. ನೀವು ಯಾವುದೇ ದೇವಸ್ಥಾನದಲ್ಲಿ ಹೋದ್ರೆ 7 ಹೆಸರು ಸಿಕ್ಕತ್ತೆ. ಆದ್ರೆ ಇನ್ನೂ ಒಂದು 8ನೇದು ಇದೆಯಂತೆ. ಅದು ನೀವು ಬರೀ ಕಣ್ಣಲ್ಲಿ ನೋಡಿದ್ರೆ ನಿಮ್ಗೆ 8ನೇದು ಕೆಲವು ಸಲ ಕಾಣಿಸುತ್ತೆ, ಕೆಲವು ಸಲ ಕಾಣಿಸೋದಿಲ್ಲ. ದಟ್ ಈಸ್ ಎ ವೇರಿಯಬಲ್ ಸ್ಟಾರ್. ಆದ್ರೆ ಕತೆ ಅಷ್ಟಕ್ಕೆ ಬಿಟ್ಬಿಡ್ಬೇಕು. ಯಾಕಂತ ಹೇಳಿದ್ರೆ ಮುಂದಕ್ಕೆ ಹೋದ್ರೆ ನನ್ ಇನ್ನೇನು ಪ್ರೂವ್ ಮಾಡಕ್ ಬರೋದಿಲ್ಲ. ಕತೆ ಅಷ್ಟೇ ಅದು. ಆ ಕತೆ ಏನ್ ಹೇಳ್ತಾರೆ ಅಂದ್ರೆ, ಸಪ್ತಮಾತೃಕೆಯರಲ್ಲಿ 7 ಜನ, ಅದರಲ್ಲಿ 6 ಜನ ಇವನು ಸ್ಕಂದ ಅಥವಾ ಕಾರ್ತಿಕೇಯನನ್ನ ನೋಡ್ಕೊಂಡವ್ರು. ಆದ್ರೆ ಪಾರ್ವತಿ ಅವನ್ಗೆ ತಾಯಿ ಆಗ್ತಾಳೆ. ಹಾಗಾಗಿ ಅದು 7ನೇದು. ಹೀಗೆ ಬರುತ್ತೆ ಹೋಗುತ್ತೆ. ಒಂದೊಂದ್ಸಲಿ ಅದನ್ನ ಸೇರ್ಸ್ಕೋಬೇಕಾಗುತ್ತೆ, ಒಂದೊಂದ್ಸಲಿ ಸೇರ್ಸ್ಕೋಬೇಕಾಗಿಲ್ಲ ಅಂತ ಅನ್ನೋ ಅರ್ಥದಲ್ಲಿ. ಇದೇ ತರ ಇದೇ ನಕ್ಷತ್ರಗಳಿಗೆ ಗ್ರೀಕ್ ನಲ್ಲಿ ಒಂದ್ ಕತೆ ಇದೆ. ಅದರಲ್ಲಿ ಇವರು 7 ಜನ ಅತ್ತಂಗಿಯರು. ಅವರಲ್ಲಿ ಒಬ್ಳು ಅಳುಬುರ್ಕಿ, ಯಾವಾಗ್ಲೂ ಅಳ್ತಿರ್ತಾಳೆ. ಅವಳು ಅಳ್ತಿರೋದ್ರಿಂದ ಅವಳು ಮುಖ ಅವಾಗವಾಗ ಕುಗ್ಗೋಗುತ್ತೆ. ಇದು ಒಂದು ಕತೆ. ಹೀಗೆ ಅವರಿಗೆ ಕಣ್ಣಿಗೆ ಏನೋ ವ್ಯತ್ಯಾಸ ಕಂಡಿದ್ದು ಕತೆ ಹೇಳಿರ್ಬೋದು. ಆದ್ರೆ ಅದನ್ನ ನಾನು ಪ್ರೂವ್ ಮಾಡಕ್ ನನ್ನ ಹತ್ರ ಏನೂ ಇಲ್ಲ. ಇದು ಬರೀ ಕತೆ, ಅದನ್ನ ಪಕ್ಕಕ್ಕಿಡೋಣ. ಕತೆ ಬಿಟ್ಬಿಟ್ಟು ಇದಕ್ ಬಂದ್ರೆ, ಗ್ರೀಕರು ಆತರ ಕತೆ ಕಟ್ಟಿದ್ರು. ಮತ್ತೆ ನೀವು ಇದಕ್ಕೆ ಮಾವೋರಿ ಜನಾಂಗಕ್ಕೆ ಹೋದ್ರೆ ಅಲ್ಲೂ ಒಂದ್ ಕತೆ ಇದೆ, 7 ಜನ ತಂಗಿಯರದ್ದು. ಆದ್ರೆ ನಾವು ಅಸ್ಟ್ರಾನಮಿಗೆ ಬಂದ್ರೆ ಈ ಅರಬ್ರು ಹೆಸರು ಕೊಟ್ಟಿದ್ದಾರೆ ನಕ್ಷತ್ರಗಳಿಗೆ. ಇಲ್ಲಿ ಒಂದ್ ನಕ್ಷತ್ರ ಇದೆ, ಆಲ್ಗಾಲ್ ಅಂತ ಒಂದ್ ನಕ್ಷತ್ರ ಇದೆ. ಇದು ಈ ನಕ್ಷತ್ರ. ಈ ನಕ್ಷತ್ರಕ್ಕೆ ಆಲ್ಗಾಲ್ ಅಂದ್ರೆ ಡೆಮಾನ್ಸೆಡ್. ಇದು ಅದು ಮೂಲ ಆಲ್ಘುಲ್ ಅಂತ ಅರಬ್ ಹೆಸರದು. ಯಾತಕ್ಕೆ ಈ ಹೆಸರು ಇಟ್ಟಿದ್ದಾರೆ ಅಂತಂದ್ರೆ, ಇದು ಒಂದು ರಾಕ್ಷಸ ಯಾವ್ದಾದ್ರು ಸರಿಯೇ, ಅದನ್ನ ಯಾರು ನೋಡಿದ್ರು ಅವ್ರು ಕಲ್ಲಾಗ್ಬಿಡ್ತಾರೆ. ಅದಕ್ಕೆ ತಕ್ಕಾಗೆ ಒಂದು ಕತೆ ಕಟ್ಟಿದ್ದಾರೆ. ಇವನೊಬ್ನು ಹೀರೋ, ಅದೆಲ್ಲ ಬೇರೆ. ಇದು ಪರ್ಸಿಯಸ್ ಅಂತ ಆಕಾಶದಲ್ಲಿ ಎಲ್ಲಿ ಕಾಣುತ್ತೆ ಅಂದ್ರೆ, ಇದು ಕೃತ್ತಿಕ, ಇದು ರೋಹಿಣಿ ಕೃತ್ತಿಕ, ಇದು ಆಲ್ಗಾಲ್, ಆಮೇಲೆ ಇದು ಅತ್ಯಂತ ಪ್ರಕಾಶಮಾನವಾದ ನಕ್ಷತ್ರ. ಇದು ಹೀಗೆ ಈ ನಕ್ಷತ್ರನ ನೋಡಿದ್ರೆ ನೀವು ಒಂದೊಂದ್ ದಿವಸ ಕಾಣುತ್ತೆ, ಒಂದೊಂದ್ ದಿವಸ ಕಾಣೋದಿಲ್ಲ. ಇದಕ್ಕೆ ಆಲ್ಗಾಲ್ ಅಂತ ಹೆಸರಿತ್ತು. ಸೊ ಈ ನಕ್ಷತ್ರ ಇನ್ನು ಮುಂದೆ ಇನ್ನೊಂದ್ಸಲಿ ನಾನು ಹೇಳ್ಬೇಕಾಗತ್ತೆ ಈ ನಕ್ಷತ್ರದ ವಿಷಯನೇ. ಇದನ್ನ ನಾವು ಬಹುಶಃ ಮೊದಲನೇ ವೇರಿಯಬಲ್ ಸ್ಟಾರ್ ಅಂತ ಕರಿಬಹುದು. ದಿ ವೆರಿ ಫಸ್ಟ್ ವೇರಿಯಬಲ್ ಸ್ಟಾರ್ ಟು ಬಿ ಡಿಸ್ಕವರ್ಡ್ ವಾಸ್ ದಿಸ್ ಅಂತ ಹೇಳ್ಬೋದು ನಾವು. ಆಮೇಲೆ ಇನ್ನೊಂದು ನಮಗೆ ತುಂಬಾ ಪರಿಚಯವಾಗಿರೋದು ಅಂದ್ರೆ ಸಪ್ತರ್ಷಿ ಮಂಡಲ. ಸಪ್ತರ್ಷಿ ಮಂಡಲದಲ್ಲಿ ಈ ನಕ್ಷತ್ರ ಇದೆಯಲ್ಲ, ಇದು ಜೋಡಿ ಇದೆ. ಅದಕ್ಕೆ ವಶಿಷ್ಠ ಅರುಂಧತಿ ಅಂತ ಕರಿತೇವೆ. ವಶಿಷ್ಠ ಅರುಂಧತಿ ಜೋಡಿ ಅಂತ ಕರಿತೇವೆ. ನೀವೊಂದು ಚಿಕ್ಕ ಟೆಲಿಸ್ಕೋಪ್ ನಿಂದ ಫೋಟೋ ತೆಗೆದ್ರೆ ಹೀಗೆ ಕಾಣುತ್ತೆ ಅದು. ಎರಡು ತುಂಬಾ ದೊಡ್ಡ ಇದರಿಂದ ತೆಗೆದ್ರು ಕೂಡ ಹೀಗೇನೆ ಕಾಣಿಸೋದು, ವ್ಯತ್ಯಾಸ ಏನು ಬರೋದಿಲ್ಲ. ಆ ಚುಕ್ಕೆನೆ ನೀವು ಬರಿ ಕಣ್ಣಲ್ಲಿ ನೋಡಿದ್ರು ಚುಕ್ಕೆ, ದೊಡ್ಡ ಹಬಲ್ ಸ್ಪೇಸ್ ಟೆಲಿಸ್ಕೋಪ್ ಅಲ್ಲಿ ನೋಡಿದ್ರು ಕೂಡ ಚುಕ್ಕೆನೆ. ಇಟ್ ಕಂಟಿನ್ಯೂಸ್ ಟು ಬಿ ಅ ಡಾಟ್. ಆದ್ರೆ ಇವಾಗ ಆಫ್ಟರ್ ಸೋ ಮೆನಿ ಇಯರ್ಸ್ ಆಫ್ ಸ್ಟಡಿ ವಿ ಹ್ಯಾವ್ ಫೌಂಡ್ ದಟ್ ಇಟ್ ಈಸ್ ಆಕ್ಚುಲಿ ಎ 6 ಸ್ಟಾರ್ ಸಿಸ್ಟಮ್. ಸೊ ನಾವು ಬರೀ ಒಂದು ಕಾಣಿಸೋದು, ಅದಕ್ಕೆ ಮಿಸಾರ್ ಆಲ್ಕಾರ್ ಅಂತ ಹೆಸರು. ಮಿಸಾರ್ ಇಸ್ ದ ಬ್ರೈಟರ್ ಒನ್, ವಸಿಷ್ಠ. This is Arundhati. Arundhati itself is a binary. Vasishtha has 2 components, and first they thought that it has 2 components just like Alkar, but then each of them turns out to be a binary. So it is not Vasishtha Arundhati, ಅವರು ಸಂಸಾರನೇ ಇದೆ ಅಲ್ಲಿ, 6 ಜನ ಇದ್ದಾರೆ ಅಲ್ಲಿ. ಹೀಗೆ it's very interesting. So this is one type of variability of position. If you observe over 1,000 years, you can notice that there is a small change in the position of Vasishtha and Arundhati, the separation between them, and so on. So now we have to define what are variable stars. What I gave as the example now are the eccentric binaries, because the variability is associated with the position. And sometimes it can be one covering the other, so it is eclipsing. Well, you have under this category spectroscopic binary and such fine subdivisions. But then we have intrinsic variable stars also. Something is happening inside the star, because of which you notice that they are pulsating or they are erupting, or periodically something is happening to them. So we broadly classify the variable stars into this, and let us try to see examples of these variabilities. Now, let us start with how to find the mass of the Earth and the mass of the Sun. You know that gravitational force is the only one that can be used for estimating the mass. So for finding the mass of the Earth, we use the fact that the moon goes around it. And from the formula, the mass of the moon gets eliminated. This is something which you all have been teaching, so this is how we estimate the mass of the Earth. Now you just replace the Earth-Moon system with the Earth-Sun system, you get the mass of the Sun. So now you can extend it to the planet Jupiter, which has satellites, or planet Saturn, which has satellites. So basically you need to know the orbital period of the satellite, and then the distance, or the orbital radius, and the velocity. And then you also have the Kepler's laws, with which you can modify this and estimate the mass very precisely. Well, when it comes to isolated stars in the sky, how do we estimate the mass? Because we only get the light from that. The light tells us about its luminosity, the light tells us about its temperature, its color, and other parameters, but not the mass if it is an isolated thing. Therefore, a star with a companion is the basic requirement. Comparable mass, that's important. If it is a Earth-Moon system, then the mass of the Earth is so small that if you go outside the solar system, you may not be able to recognize the motion of the Earth around the Sun at all. So if the Earth is replaced by another sun, what may happen? Now you perhaps give this as a problem for students, and then you get the answer ignoring the fact that the velocity also is governed, and then the common center of mass is the one that you have to consider, etc. It's all that is part of the classroom thing. Such an idea was first proposed by John Goodrich. He was a very young astronomer, and there is a plaque also. He died very young. At the age of 16, he became a member of the Royal Society at the age of 18 itself, because he found that the star Algol, which I had shown earlier, is a variable. He was deaf and dumb, and observing the sky was his hobby. And he monitored the variation of the light and said that there is a periodicity associated with it. And that should be possible only if there is another star which is going around it. So he was the first to propose the idea of a binary thing, which was not well received. So this is the animation of what he proposed. Of course, the animation is recent, and we will come to Algol again later, because Algol is not such a simple system. So the idea of a binary star, and because of that, the light showing variation, was first proposed by Goodrich, and he called this eclipsing binary. And the moment you have eclipses, you can also consider the red shift and the blue shift as the star is coming towards you and going away from you. So such stars are called spectroscopic binaries. And eclipsing is also invariably a spectroscopic binary. And if they are both going around the common center of mass, one star is coming towards you and simultaneously other star is going away from you. So the spectral line, one will show the blue shift, the other will show the red shift. That is called double line spectroscopic binary. So this proved a great boon for establishing the mass of the star, because once you have the periodicity established, and if you are able to estimate the distances, though not very accurately, you can get an idea of the masses that are involved, because you can apply modified law of the Kepler. Now comes the question of why mass should be studied. Now you all have a rough idea of the sequence of stellar evolution. So it all originates with the nebula, and then depending on the mass, today we know that the path followed is it becomes an adult on the main sequence, then a red giant, then a planetary nebula, and the white dwarf. This is what we know now. Now, similarly, high mass stars will become red supergiants, and it explodes as a supernova, which can result into a neutron star or a black hole. Now, to prepare this one slide now, it's very easy. You Google anywhere, you will get it. But it involved the basic knowledge of the mass of the star, because it's the mass that decides what should be the path that will be taken by the evolution. So the knowledge on mass is very important, basically in understanding the life cycle, but it also provided a hint on the mass being responsible for the intrinsic properties and the lifespan of the stars. Unlike the biological systems, a massive star will live for a shorter time as compared to a less massive star, which will live for billions of years, which is directly related to the process of energy generation. So you know that this is the sequence of mass increasing, the luminosity increases in this direction, the temperature increases in this direction, and so is the mass. So the larger the mass, the brighter the star, the larger the star, the hotter the star. So the sun being somewhere here is an average star, and there are stars which are cooler and which are less massive than the sun. So that resulted in what is called a mass luminosity law, about which you know, which looks a beautiful straight line on first glance. But when you start adding more number of points, you will notice that the variation is different. It is to the power of 2.7 here, 4.7 here, and 3 point something here. So what decides these differences? Why there is a difference? Why all the stars are not producing the luminosity simply as a linear variation with the mass? So this question was addressed about 100 years ago in a very different way, because 100 years ago we came to know that nuclear fusion is the one that is responsible for this. So we know this is the energy process, the proton-proton cycle, and now we also know the CNO cycle. So it turns out that for very low mass stars, sun and less massive stars, it is a PP chain which is predominant, and in higher mass stars, it is the CNO cycle. So this basic difference was understood 100 years ago, not exactly 100, a little later, maybe 80 years ago. And then the studies on the evolution took a different turn. And so we have that huge branch of nucleosynthesis inside the stars and so on, and the evolution itself. So the binary stars are important because, as I mentioned, it resulted in the mass luminosity law. So if you have an isolated star now, you can go to the mass luminosity law and then get the mass of the star. It also resulted in the discovery of a white dwarf, the very first white dwarf, when Chandrasekhar proposed it. It was only on the book, but the first case of establishing it in the sky was with the help of the brightest star in the sky called Sirius. The variability was not in light, but it was in the position. As you can see here, over about 100, this is first one is 1866. Onward, they started noticing that Sirius is changing the position. All the other stars will be going in straight. This is the proper motion of stars, which you will be able to appreciate over only hundreds of years. Sirius, instead of going in a straight line, was going in a wavy manner like this. And this could not be explained in any other process other than hypothesizing a companion. So, if you assume that Sirius has a companion, and because of the companion, it is taking a path like this in the sky, the dashed line here is the one for the center of mass. So now you can estimate what is the mass of the other star, which is probably its companion. It turns out to be about 1 solar mass. But 1 solar mass is a star that should be like the sun, but it's not visible. And many attempts to photograph it in the pre-Hubble space era were not very successful, basically because Sirius is so bright. But that turned out to be a challenge. But still, now you have a star which is one solar mass, but not so bright as the sun. So that was the white dwarf that fitted with the white dwarf. And so this was the first white dwarf that was discovered. It is called now Sirius B, the companion of this. Similarly, the detection of neutron stars. Neutron stars are not visible. So there again, it was the binary systems wherein you get the estimate the mass of the star, and that turns out to be something like 2 solar masses, but not on the main sequence. Similarly, even the establishing a black hole as a kind of an object. I don't know whether I'm justified in calling the black hole as an object, but there is a mass there, and it is going around a star which is visible. So the visible star will show these kinds of variations, and based on that you estimate the mass, and that turns out to be the black hole mass. And very recently, few years ago, they were very successful in detecting the black hole at the center of the Milky Way. And that was possible because there were so many stars that were going around the black hole, and putting all the different orbital periods together, they were able to find that yes, there is a black hole, and they were able to estimate the mass also. So this is the process that tells us the clue that there is a neutron star because it emits X-rays because of this accretion disk and other phenomena associated with it. Similarly, black holes also. So these are neutrons, black hole binaries and neutron binaries. So binary stars are very important in these kinds of studies. Now let us go to the other types of variables. Now this is the main sequence. Most of the stars you expect to be very well behaved and be here. But this is the region of supergiants and hypergiants. This is the famous HR diagram. So all the stars are generally found on the main sequence. But you have plenty of stars which are in this domain where they are variable. They show variability. So delta Cepheids, beta Cepheids, RB tau, these are all the names of the variable stars. The bright stars are given alpha, beta, gamma, delta. But the variable stars are given names starting with P. P Cygnus, for example, is the first variable star discovered in the constellation of Cygnus. And T Tauri is PQRST, that variable star in the constellation of Tauri, and so on, Taurus. And so some of them have names and some of them have these kinds of names. Now the number has increased so much that they just give V1506 Cygnus. So that's the kind of numbers we are encountering in kinds of variable stars. So basically the idea is that they are appearing at a place which is neither main sequence nor the domain of supergiant, somewhere in between. This is the region where most of them are deviating from the normal trend, and so all the variable stars are generally associated with this. So I'll give examples from different parts of the main sequence. So we have variable stars here, we have variable stars here, we have variable stars here, and so on. And these are the magnetic field variables. So you know how the magnetic field can be identified in spectra using the Zeeman shift. So there are many magnetic variables in this domain, and this is the most massive of the stars. The Wolf-Rayet star has an extended atmosphere. It is deficient of hydrogen. There is no hydrogen in this. So what happened to the hydrogen, we do not know. They appear in this region, and what you see in the extended atmosphere are all ionized carbon, ionized nitrogen, and N3, C3, C4, and of course helium. And generally they will have a O-type star as a companion. The very fact that you see a Wolf-Rayet star in a specific region means that that was found very recently, because this is the domain where the lifespan is of the order of say 10 million years, 100 million years. So the fact that you see this means that it was a young star which was formed very recently. And they show variability in case of the extent of the atmosphere, and many of them are binaries. Then we have the BE stars, which are not as massive and as hot as the Wolf-Rayet stars or the O-type stars. They have an extended atmosphere and they show emission lines. And the emission lines, generally you see the absorption lines, the Fraunhofer's discovery, you know. So in the spectrum, you will see extended atmosphere and emission lines. This is normal B star will not show that, but this has an extended region. So what is the reason to see this extended atmosphere? So that you will be able to study with this kind of thing. Why a normal B star will not show the emission lines, but this will show. So this is a very interesting field of study. When you have many other stars which are cooler, like the sun, or slightly hotter, they all show excess abundance of metallic lines like mercury, manganese, and silicon. And you expect the metallic lines to be in this part A, F, G, K. And they also show chromospheric activity just as the sun does. And magnetic field variation. The magnetic field is 10 to 100 times that of the sun. So we have to understand why all these things are happening, why there is a trend which is different from that of the main sequence stars. And just as we say excess abundance, we see some deficiency also. Hydrogen is deficient in some cases. And there was a conference in Mysore. It was called hydrogen deficient stars. It was on hydrogen deficient stars. So there were many, because it was an international conference. On the first day, there was a press meet. There were many press people who came, and they were worried about the word deficient. They thought iron is deficient, So if you then I can give you capsule if you have iron deficiency. What will they do for the stars? Now, this is the kind of worry they had. And they were wanting to know by in this conference whether we were doing anything for correcting the deficiency or something. That was very funny. But anyway, we are trying to understand why they are deficient. This is there are many stars which have this kind of deficiency. And Sun is not a very quiet star. You know that. It has a periodicity of 11 years and then it has an extended corona. This is the flash spectrum taken during the total solar eclipse, where all the bright lines are seen because originating in the corona and so on. This is the beautiful butterfly diagram which shows the variation of the sunspot cycle. In the case of the sun, the area, the surface area of the sun, which is covered by the spots, is just about 5%. But there are stars where you have the spots covering it almost 40%. Then this kind of a variation is extremely large and they show up in different ways, not only in the magnetic variation, but also in the light variation itself. When the sunspot covers the sun, we don't see much of a variation in the visible. We see it in the X-ray, but in these stars which are having chromospheric activity, you will notice that even the light itself is diminished. So this is another interesting thing, and most of them are binaries. So that adds to the complications. So the corona gets pulled because of the tidal distortion and so on. Then we have these pulsating variables, and as I mentioned earlier, the Cepheids, these are the names. Now, Cepheid is a prototype star. RR Lyrae is the prototype, and if when you see many more, they all will be grouped into that. And you have long period variables. I showed you the HR diagram. They are all in this region only. Cepheids is one thing very important. So the Cepheids variables were Cepheid is the star Delta Cepheus. In the constellation of Cepheus, it's the fourth bright star. That's how it gets the name. And Henrietta Leavitt, and now they call it a computer data analyst. These are very strong words. Those days they were doing all with paper and pencil. There was no computer. She was called a computer. She made observations of more than 2,500 variables of this type. And she got the periodicity and she came up with a very important result. That result was that they have a very regular relation with the luminosity. If it is a very bright Cepheid, its pulsating period also is very high. If it is not so bright, then its pulsation period is also not very high. So now you see here the trend. These are the Cepheids of the Milky Way, and these are the Cepheids of the LMC, Large Magellanic Cloud, which is our neighboring galaxy. When she studied this and established this, it was a revolution. Now we have a mechanism of finding the distance to the whatever region we are looking at. Now, there was no way of proving that Large Magellanic Cloud is a different galaxy. But then how do we establish it? Now, according to this, the luminosity should be decided by the period. So let's say that this is the period and we decide that this is the luminosity. But the actual luminosity that you measure is different. So you can only attribute it to the distance. So you can estimate how far it is, and it's not a member of the Milky Way. You will get a number which will push it out of the Milky Way. So she was able to pinpoint and say that this Large Magellanic Cloud is not part of the Milky Way. And this the estimation of this distance, so this is a pulsating variable, and this she was able to give as a boon to the later study. Most importantly, the work of Hubble. When he tried to estimate the distances for different galaxies, he picked up the Cepheids in that region and he was able to establish the distance, or somebody had established the distance and he used them. So he was able to relate the redshift to the distance. That's how the law developed. And then there are other mechanisms also for finding the distance, but this was one of the most important things. Then we have the exploding stars. So you know that there is a core collapse of the star, and then the ultimate fate of the massive stars is, when I say massive stars, mass more than 8 solar masses, that will explode as a supernova. Okay, so this is what is understood already, so I don't have to spend time on this. A massive star will evolve into a supergiant so that it has a Fe-Ni core. Then you have silicon, oxygen, neon, magnesium, carbon, helium, all these things in the onion-like structure. And when the nuclear fusion burns here, so ultimately when iron is formed, these time scales are all calculatable, and so when you finally notice that it explodes and it becomes a supernova. So that's the animation showing how this is called type 2. Why did I call this type 2 as the first one? So there is a type 1 also. So the type 1 supernova and nova, they have this kind of a mechanism. So it's a binary system. And so there is mass accretion from the evolved star which throws material onto this. And so there is an accretion disk that is formed, and the accretion disk can yield interesting consequences. So one of them is the nova, which is a periodical thing. So the star becomes very bright. And now when I say star, both of these two put together will appear like a single dot even through the largest telescope. So what you notice through the telescope is that there is a dot which suddenly becomes very bright. And all this simulation that you are showing here is all based on the studies. But what you see in the sky is a single dot. So a single dot will suddenly increase in brightness, so it may become visible to the naked eye, and it may stay for 10 days, it may stay for a few hours, and then it will go back to its quiescent brightness. On the other hand, if it's a supernova, then it can be there for maybe 8 to 10 months, it's visible. So based on this criterion, they are generally classified as cataclysmic variables. You have novae, recurrent novae, dwarf novae, based on the period. For example, right now there is people are waiting for a particular recurrent nova to explode, which is known to have a period of about 80 years. So this is the kind of interest it generates, and each turns out to be a unique system. So you will have to study the mass exchange phenomena and then the rate of accretion and how the accretion disk ultimately results in producing these kinds of mechanisms and make it visible to the naked eye. What you see is that in the region in the sky where there was no star till yesterday, so today suddenly a dot has appeared, and it may not be there after a few months. But still, we have not understood all of it. Now here I am showing the Algol. Algol has been studied in the last few decades with the space telescopes, and they find that after all, it may not be a binary. It seems to be doing some thing because of which it's throwing out material periodically. Or is there another star at all? So this eclipse which John Goodrich studied and declared that there is an eclipse, yes, that is true. There is periodicity, there is an eclipse. But it may not be another star. This star itself is doing something. So these are simulations based on observations from the Hubble Space Telescope. So this is a challenge. You have to yet understand this. Then there is another star, this one. Now you see the time scale also there. In the last 36 years, it has been observed carefully and it's doing something. It's a huge star. Betelgeuse is a huge star, 100 times the size of the sun, 100 times the radius, let's say. So something is happening in its interior, because of which it is showing some activity on the photosphere. We recognize as a periodical variation in brightness. 2 years ago, it suddenly disappeared. When I say disappeared, it was not visible to the naked eye for a few months. Then it reappeared, it regained the brightness. So why is this happening? So what is the interior mechanism that is responsible for this? So we need to understand these things. So these are the challenges that are offered by the variable stars. Let us go to our nearest neighbor, the Alpha Centauri system. Alpha Centauri itself is a double. That was known, that in fact that was discovered in India. These Europeans did not have access to see the southern skies. So when they came to India, they were very thrilled that they can see so many new stars and a lot of interesting objects in the southern sky. So this Alpha Centauri was studied very meticulously with a small telescope. No, they did not bring a large telescope. Some 300 years ago, a Jesuit observer who came as a missionary, he established that this is a binary system. So that is this Alpha Centauri A and B. But subsequently, they found, 100 years ago, they found that there is another star which is going in an elliptical orbit around this. This is Proxima Centauri, and because of this elliptical orbit, it comes closer to the solar system than the other two once in a while, and therefore this is called Proxima Centauri. So this is A, B, C. Now, have we understood this system? This is the nearest system. Have we understood this as a variable star? No, because that is a case of a planet. Whether Proxima Centauri has a planet, that is the subject of study, and yes, they have found something. So that takes us to the field of extrasolar planets, where we need to find whether there are planets for other stars. Well, the idea is that if Earth passes in front of the sun, and if you are sitting on Jupiter and watching, there is no change in the brightness of the sun. On the other hand, if Jupiter were to pass in front of the sun, and if you are sitting somewhere beyond Jupiter, then there is definitely a change in the brightness. Therefore, you can detect the planets when there is a transit. Just as Venus went in front of the sun some 12 years ago, we all had seen it. Similarly, if there is a large planet which is passing in front of the sun, that phenomena, which we call as the transit, can be used to find the extrasolar planets. That means we have to know whether it's a variable, whether it is showing any variation at all. So this mission called Kepler was sent exclusively for studying the transits of possible planets in front of the stars. And so there were some candidates that were selected, and it started reporting results. It started reporting results on multiple systems like this. There are 2 planets going in front of the thing, so it's a multiple planet system. Now this study is has assumed large dimensions. They have involved some other methods also to find the extrasolar planets, not only the variability of the brightness. So this is the exoplanet discoveries, and as you can see, already some 3,500 extra planets have been discovered, and so this many of them are in this of the size of Jupiter and Neptune, and they have found some Earth-like things also. So once in a while, you keep hearing that they have found an Earth-sized planet elsewhere, some light years. This is as on December 14, 2017. Today, I think the whole thing will be filled with many more dots. Okay. So this is where the variability of the star gains very important thing. And I should mention here about this star called 70 Virginis. That's the 70th star in order of brightness. I don't know, maybe it is 70 or 71 in the constellation of Virgo. There was an observer called Jacob in Madras Observatory 150 years ago. He was observing this. They were monitoring the variable stars. In fact, the Madras Observatory was very well known for its catalog of stars. And so this person, when he observed this star, he noticed that there is a small variation in brightness. It was very small, so he did not have a very large telescope. He had only a small 6-inch or 8-inch telescope. But he put a note saying that there is something special about this. It has a variation, but I am not able to establish whether it has a companion. And it was one of the first stars for which an exoplanet was discovered in the 90s. For establishing a planet, you need minimum of 20 years. You need 20 years to notice that there is a variation. You need another 20 years to show that yes, it is correct. So it's a very slow process, and finally now we have such a large list. If you are using only the transit method, now there are other methods, and based on that, so many planets have been discovered. So why are the variable stars important? As I mentioned, estimation of the mass and understanding the life cycles of stars, the variable stars have contributed a lot. The mechanism of energy production and the interior processes we need to understand. And now for the detection of planets outside the solar system also. And finally, understanding the structure of the Milky Way and other galaxies where Cepheid-like variables have contributed a lot. So this is where I'm concluding. And thank you for giving me this opportunity to talk to physics people. And so, thank you.
Thank you very much, madam. Would you be willing to take some questions on this
Yes,
particular
definitely,
topic?
definitely.
Okay, now time is available for some questions. Anybody would like to ask a question, you may do so one by one, please. Anybody? Okay, to start with, I have a question.
Please.
I was reading about white dwarfs to some extent. I noticed that even white dwarfs have got some variability. DAV and DB. How
Yes.
does one ever explain something like a dead star having variability? What kind of a mechanism would be there?
I don't know. In fact, there are 3 types of white dwarfs: helium white dwarfs,
Yeah.
oxygen neon magnesium white dwarf, carbon oxygen white dwarf.
Yes.
That you can attribute to the mass. But then this variability is whether it is still cooling or it's a very recent one. I do not know whether that kind of a thing is responsible for the variability in white dwarfs.
Very puzzling thing. Okay, Professor Paniveni Uday Shankar, you may ask question.
I was only wondering whether
Okay.
the
Hello?
distance ladder has that changed overall since we talked about the expansion of the universe happening at an
Definitely.
accelerated phase was going on in my mind when you spoke about the Cepheid variables and the beginning of a distance ladder from it.
Yes, yes. Yeah, that's quite natural because that was the starting point for Hubble. Now you have many other mechanisms for extending the distance ladder. See, first you can do only for nearby galaxies. How will you use this method? So you
No,
have
not
to
Cepheid variables. They use supernova remnants to look
supernova.
at
Now
them.
they have become candles now. So
Yeah,
okay,
correct.
that
So what I was asking is,
type one supernovae have replaced Cepheids now.
yeah,
But
it depends
Cepheids
upon the
was the starting
distance.
point.
Yeah.
Yes, yes.
Now, I was wondering whether there is any additional new information which has come on the distance ladder, because people are talking about non-standard models of cosmology, and
Oh,
distance
no.
ladder is the basis
I,
for it, and the Cepheids are the basis for the distance ladder. It was a question, I mean, in a very general way, not
no,
exactly connected
I
with
didn't,
the.
yeah, I didn't want to include any part of that here because I was working only on the contribution of the variable stars.
Yeah, no, fair enough, fair enough. No, it was just going on in my mind. That's all.
Okay, okay.
When he, thank you very much
So,
for telling us,
Okay.
and also your slides are extremely nice and very nice, very colorful and very, very catchy. That's very important, for us to
Okay.
keep on thing in a Zoom.
Dr. Paniveni, would you like to ask
Yes.
questions? Please.
Very interesting talk, Madam. Dr. Shylaja.
Thank you. Thank you, Paniveni. I'm
uh,
hearing your voice after a long time. You have stopped singing.
You mentioned about yes.
At
You
least I heard
mentioned
your
about
voice singing somewhere,
Okay, go to question, please.
Question, please.
yeah. You mentioned about metal content. If it is more in a star, and then it can be also less in another star, another group of stars, etc. Metal content rich stars are known as population 2 stars, if I'm right.
No.
Is it?
I'm now talking only about the main sequence stars. Population 1 or population 2, that is a different mechanism. Here, what you notice is that suddenly there is an increase in the abundance. It's a A-type star. It's a A-type star, population 1. It's part of the same cluster, let's say. But there, among all the A-type stars, there is one star which shows excess of manganese. In our own Milky Way, they are all within 40, 50 light years. But suddenly there is one star which shows excess of silicon. So why are they isolated cases? There are not many of them, about say 100. So the distinction for population 1 or population 2 takes you to the clusters, open clusters and globular clusters. These are not members of clusters. These are isolated stars. That's why they're puzzling. It's puzzling why they are showing overabundance of a specific metal or underabundance. That is also there. So
And
they
another
were
thing is
mercury manganese stars. They were classified as mercury manganese stars. Okay.
Yeah.
Yes.
Okay, thank you. Another one that you mentioned was this Betelgeuse, which is a red giant star. I think
Yeah,
so.
it is.
Right?
It's a red supergiant.
Red giant star in the end stage of its life, right?
So
it was not visible at all for some time. You said
no. It is very much It is very much visible. Its brightness decreased. It's so striking. You can't miss it. It's so bright.
Yeah.
So any person can see it in the sky without any guidance. It's so bright. But suddenly it became dim. That's all. From say second magnitude, it became fourth magnitude.
What could have been the reason?
No, that's what I showed. That final animation that I showed is based on the decrease in brightness in the last, say, few years. They have combined all that, and this is the only star for which interferometry was possible to estimate its size. No, otherwise you can't estimate the size of a star at all. You can't get the radius of a star. But this is so big. This is 100 times the radius of the sun. So they use the technique of interferometry for this and estimated the size and extended that now to show that the star is pulsating. That's the animation that I showed.
Oh my. Okay. Thank you. Thank you.
Kagli sir.
Okay, here is Professor Vijay Kumar.
Interact with Shylaja madam.
Yes.
Queries and yeah, madam, it was very nice talk. And as said by Professor Uday Shankar sir, some of the slides were very good, really nice, good information. So now coming to the my questions and comments, the exoplanets number now has gone to 6,000 currently.
Yes, yeah, I showed a whole slide. It was
that is one thing. And Professor Uday Shankar sir was talking about the distance ladder. And now the distance ladder is extended with the study of the active galaxies.
in which,
Yes.
yeah, because
Supernovae are the ones.
Yeah,
yeah,
Supernova is the one.
Doppler shift and redshift, and probably the observable now the redshift has been up to Z12 or so.
Yes.
And this
So
establishes the age of the universe very close to the Big Bang event.
definitely.
Yeah,
But
0.5.
that's not the contribution of the variable stars. Okay, that
Right.
is a different thing
Yeah.
altogether. That's why I did not
Cosmology,
include
that's
that.
cosmology.
Yes, madam. Yeah, variable stars contribution is for the Andromeda and like
Yes,
very
yes.
external
Nearby
galaxies.
galaxies.
Nearby galaxies only.
Nearby galaxies.
Fixed galaxies and all that. Anyway, it was very nice talk, madam. Thank you very much.
Thank you.
I'm interested in some of your slides to use it for my class with MSc students.
Now it is it's recorded, I think, isn't it?
No,
I have it's all
you
from this.
share for it. If you share it with me, I will share it with the people who are interested.
Yes,
No,
sir.
these are all, I took them from
Very
internet.
simple.
They are all, I have given this thing also somewhere.
Yeah, I request you to share it later, madam. It's so.
ಇನ್ನೊಂದು ಐ ಹ್ಯಾವ್ ಎ ಸಿಂಪಲ್ ಕಾಮೆಂಟ್. ಈಗ ಸ್ಟಾರ್ಸ್ ಬಿಯಾಂಡ್ ಸನ್ ಏನಾಗ್ತವೆ, ದೇ ಆಲ್ ಪಾಸ್ ಥ್ರೂ ದಿ ಅಸಿಂಪ್ಟಾಟಿಕ್ ಫೇಸ್. ರೆಡ್ ಜಾಯಿಂಟ್ ಫೇಸ್ ಪಾಸ್ ಆಗ್ತದಲ್ಲ, ಅದನ್ನ ದೇ ಮಸ್ಟ್ ಆಲ್ ಬಿ ವೇರಿಯಬಲ್ ಅಂತ ನನಗೆ ಅನ್ಸುತ್ತೆ.
ಹೌದಾ, ದಟ್ಸ್ ದ ರೀಸನ್. ಅದನ್ನೇ ನಾನು ತೋರಿಸಿದ್ದು.
ವೆರಿ ಲಾರ್ಜ್ ನಂಬರ್ ಆಫ್ ಸ್ಟಾರ್ಸ್.
ಅಸಿಂಪ್ಟೋಟಿಕ್ ಬ್ರಾಂಚ್ ಅಲ್ಲೇನೆ, ಹಾರಿಜಾಂಟಲ್ ಬ್ರಾಂಚ್ ಅಲ್ಲೇನೆ ಎಲ್ಲ ವೇರಿಯಬಲ್ಸ್ ಇರೋದು. ನೇಮ್ ಎನಿ ವೇರಿಯಬಲ್ ದೇರ್ ಆಲ್ ದೇರ್. ಆರ್ ಲೈರೆ ತಗೊಳ್ಳಿ, ಸೆಫೈಟ್ ತಗೊಳ್ಳಿ, ಡೆಲ್ಟಾ ಸಿಫಿ ತಗೊಳ್ಳಿ, ಎಲ್ಲವೂ ಅಲ್ಲೇ ಇರೋದು.
ವೆರಿ ಲಾರ್ಜ್ ನಂಬರ್ ಆಫ್ ವೇರಿಯಬಲ್ ಸ್ಟಾರ್ಸ್ ಟು ಸ್ಟಡಿ.
ಎಸ್, ಇಟ್ಸ್ ದ ಡೊಮೈನ್ ಆಫ್ ವೇರಿಯಬಲ್ ಸ್ಟಾರ್. ಎಲ್ಲ ವೇರಿಯಬಲ್ ಸ್ಟಾರ್ಸ್ ಅಲ್ಲೇ ಇರೋದು.
T Tauri stars are very young stars, they will be just forming the stars.
ಅದು ಸ್ವಲ್ಪ ಆಚೆ ಕಡೆ ಇದೆ. ಬಟ್ HR ಡಯಾಗ್ರಾಮ್ ನಲ್ಲಿ ನೀವು ಅಸಿಂಪ್ಟೋಟಿಕ್ ಬ್ರಾಂಚ್ ಅಂತ ಯಾವ್ದನ್ನ ಐಡೆಂಟಿಫೈ ಮಾಡ್ತೀರಿ, ಈ ಎಲ್ಲ ವೇರಿಯಬಲ್ ಸ್ಟಾರ್ಸ್ ಪಲ್ಸೇಟಿಂಗ್ ಇರ್ಲಿ, ಲಾಂಗ್ ಪೀರಿಯಡ್ ಇರ್ಲಿ, ಅಥವಾ ಇವಾಗ ಬ್ಲೂ ಸ್ಟ್ರಾಗ್ಲರ್ಸ್ ಅಂತಾರೆ, ಎಲ್ಲವೂ ಆ ರೀಸನ್ ಅಲ್ಲೇ ಬರೋದು. ಹೌದು. ಅಂದ್ರೆ ಒಂದು ಪ್ರೋಟೋಟೈಪ್ ಇಟ್ಬಿಟ್ಟು ಹೆಸರು ಕೊಟ್ಟಿದ್ದಾರೆ. ಇವಾಗ ಆರ್ ಲೈರೆ ಅಂತ ಹೆಸರು ಕೊಟ್ರು. ಆರ್ ಲೈರೆ ಅಂತ ಹೆಸರು ಕೊಟ್ಬಿಟ್ಟು ದೆನ್ ದೇ ಸ್ಟಾರ್ಟೆಡ್ ಕಲೆಕ್ಟಿಂಗ್ ಆಲ್ ಸ್ಟಾರ್ಸ್ ವಿಚ್ ಬಿಹೇವ್ ಲೈಕ್ ದಟ್. ದೇ ಆರ್ ಸ್ಲೈಟ್ಲಿ ಡಿಫರೆಂಟ್ ಫ್ರಮ್ ದಿ ಸಿಫೈಟ್ಸ್ ಅಷ್ಟೇ. ನಾವು ಆರ್ ಲೈರೆ ಒಳಗೆ ಇವಾಗ A B ಎಲ್ಲ ಬಂತು. ಆರ್ ಲೈರೆ A, ಆರ್ ಲೈರೆ B ಅಂತ ಬಂತು. ಬಿಕಾಸ್ ದೇರ್ ಆರ್ ಸಮ್ ಸಟಲ್ ಡಿಫರೆನ್ಸಸ್ ವಿದಿನ್ ದಟ್ ಗ್ರೂಪ್. ಸೊ ದಟ್ ವೇ ಈಚ್ ವೇರಿಯಬಲ್ ಸ್ಟಾರ್ ಈಸ್ ಯುನೀಕ್. ಅದರದ್ದೇ ಒಂದು ಬೇರೆ ಇರುತ್ತೆ.
Any other questions? Okay, if no further questions are there, on behalf of KPA and all of you, I would like to thank Dr. Shylaja for a very interesting and very informative talk. So thank you, madam. I thank all of you for attending the seminar and participating very actively. I would also like to thank our life member, Dr. Raghavendra, for providing a Zoom link without any fare, regularly as usual. And thank you all. And also thanks to SV Raman for providing the YouTube link. He's providing broadcasting, YouTube live broadcasting, he's providing for us. So thanks to him also. So thank you very much. Now we are closing. Again, we'll meet.
Thank you all. This was a very interesting discussion we had, and I met so many people whom I knew already. I wish I could see their faces. They are not cameras on.
Thank you.
Thanks a lot, madam.
Yeah.
We are leaving the meeting now. Please join next week for another talk. Thanks a lot.
Thank you.
No, because I'm taking.
Should I click end meeting for all? I don't know. I will do.